Hello, I'm Chris Jones from Team Thermos. Today, I, along with my teammates, David, Michelle, and John, will be presenting our idea and design for a small-scale solar thermal power plant. While looking at the world around us, we noticed how a black body would warm in sunlight, no matter the ambient temperature. This led us to question if we could build a sustainable and environmentally friendly power plant from the thermal energy afforded to us by the sun. As our discussions progressed, a second key element emerged. Whatever we designed needed to be scalable. The cooling side of the plant was rather cut and dry. Ground loop cooling system, a tried and true, environmentally sound practice used primarily in residential HVAC. We knew this could be easily adapted and scaled. As for the heat source, several ideas for a black body or thermal collector were discussed, but we didn't know if it was even possible to capture enough heat to generate power. We found many instances of commercial collectors, but they were all using concentrated solar. We were interested in a black body, like a rooftop, a parking lot, or a driveway. The black body idea led us to look at commercial solar water heaters for residential use. They are primarily of three types. There were two types that we were really interested in. They were the flat plate and the evacuated tube. Both were readily available and could help expand our understanding. While the available collectors were a proven heat source, we also kept circling back to our original idea of a large black surface. So moving forward, we began testing. We have acquired an evacuated tube solar heater demo unit, and here at my location in Southern California, have been running several tests, using a Raspberry Pi microcomputer and thermocouples. We also built a section of simulated blacktop with 50 feet of copper tubing embedded within. We have performed numerous tests over the course of the last few months to gather data about the feasibility of our concept. These include open and closed loop tests in various tube configurations, in addition to open and closed loop testing of the asphalt. We plan on continuing to test to further validate our findings. The data gathered and the simulation efforts together have shown that the design is possible. To further break down the data and the results we acquired, here is David.
Thanks, Chris. There have been three primary focus areas for our data collection. Is our design scalable? Does the change in temperature through our design closely track a change in ambient temperature, solar irradiance, or some other factor? And finally, do we get consistent and mathematically predictable heating effect through our closed loop system? To solve the first question, we reconfigured the commercial evacuated tubes to allow for open loop testing through 1, 2, 3, and 4 tubes. In ideal conditions, we're hoping to see that indeed more tubes would clearly lead to more heating through our system. Unfortunately for us, though, setting our design outside during the day, we experience day-to-day and even hour-to-hour ambient temperature and solar irradiance condition fluctuations, and that made the data much harder to interpret than we expected. If we consider outliers in each data set, it appears that 75% of our testing configurations demonstrate an upward trend in heat when tubes are added. In fact, the outliers that you see on the screen there may be rightfully interpreted as the system having a very finely tuned response to the change in solar irradiance over time. Our data suggests that steep solar irradiance climbs and falls attribute to higher and lower system temperature. In fact, the solar irradiance velocity seems to have a greater effect on our system for its size than scaling the system up or down does. After conducting the open loop tests, we closed the loop to see if our average change in temperature would grow linearly with every pass through the system, proportional to flow rate. Our data suggests that nearly linear growth in heat was achievable through our system, creating a mathematically predictable system, and we know it will be possible to simulate this in software. Since we ran the system with no heating load, however, no refrigerant working fluid for the turbine, we don't know what the rise time and settling time of our system is yet. That information is still being contemplated at this time. Knowing that variable flow rate through the closed loop would be our control mechanism, Michelle's been tackling the design of a driver interface that will modulate the speed of our system's pump. Here's Michelle to speak more on that topic.
Thank you, David. While trying to figure out how to control our working fluid through our system to achieve the maximum gradient temperature difference, it was suggested to Team Thermos by our mentor, Mr. Tom Potts, to build a low side pump driver. It was a no brainer to continue to use the Raspberry Pi to drive the gate input of a MOSFET. The whole catch was finding a MOSFET that had a low gate to source voltage but a high drain to source voltage in order to drive a pump of to different varying speeds by varying its voltage input to that pump. Now, in order to protect the MOSFET, we put a zener in parallel to protect it from the feedback of the pump varying or shutting off or turning on. Well, it is official. The low side pump driver has been built and has finally made its trip over to California and arrived this week. And this now will be integrated into our current test setup that we are using to collect our data collection right now. How we're going to do this is we're going to write a Python script. That Python script is going to read two I2C K thermocouple amplifiers and compare those temperatures to the optimal range that we want our working fluid to get our max output. And so if it's not within the range that we need we're going to vary the pump by varying the gate inputs to either slow the fluid down or increase it. Now, for our final hardware demo build, this will include our current test setup of our evacuated tubes and also the Raspberry Pi and a heat exchanger, which is still yet to be determined to put a load on our system to see how it actually performs. Now I'm going to switch over to our budget. Our original budget was about $150 less than what we currently are at. There was a little bit that had to do with this. One was we had to buy extra evacuated tubes. We tried 3 different times to get evacuated tubes delivered to California. All 3 times the tubes showed up shattered. Also, we kind of extended our scope just a little bit and went back to our original thing and decided to try to see if we could build our own black body using asphalt. So there was some extra cost put in there for us. Other than that, we have stayed on par pretty much to exactly what was originally in the budget. Now I'm going to turn it over to John to give you an update on the power plant simulation and what we plan to achieve by the end of this semester.
Thanks, Michelle. Up to this point, our team has outlined how we plan on generating heat from collecting solar irradiance. Michelle has even described our final deliverable, a pump driver that can control the flow rate and temperature of the fluid leaving our black body. Converting this consistent temperature change into electrical power is where I come in. If the pump driver can successfully control the temperature of the fluid leaving our black body, then by using the possibility of scaling that we've been testing and a readily available organic working fluid, it's possible to construct a solar thermal power plant. We would like this design to generate 1 kilowatt during the heat of the day. Ideally, it would be no larger than a residential driveway for the asphalt, or no larger than 1 meter squared for the evacuated tubes. This is the average size of photovoltaic panels of equal power capacity. Further tests and data analysis will give us a better idea if these sizes are realistic. The necessary temperature gradient to hit 1 kilowatt was determined by using an ideal Rankine cycle formula for 6 different working fluids at various temperatures. Part of the MATLAB code for isobutane is shown here. One hiccup in this approach is that due to the fluid's unique saturation curves, the given turbine outlet entropy for many of the fluids was above the saturation curve. Where available, superheated tables were used, but this problem persisted. As a workaround, the steam quality was manually changed out to 100%. However, this was a patch that, when turbine and pump efficiencies were ideal, caused the thermal efficiency of the system to be larger than that of the Carnot. The calculation was okay for an approximation of minimum temperature, but it needed to be improved upon for more accurate modeling. Through further research and using dry fluids, and the open source database Coolbra, these calculations have been reevaluated and their results were presented in our progress report. After the temperature parameters were established, the team moved on to modeling. The open source software DWSim has a thermodynamic modeling package that also uses the CoolProp database. Here is a basic model of that power plant with your pump, evaporator, turbine, and condenser. As you can see, it is a closed loop system, and based on the model for isobutane, it can run many iterations without fail. The team is in the process of developing a more complex physical model in Simscape, but if this fails, they may cycle back to DWSim to improve upon this model. Simscape is a physical modeling toolbox developed by MATLAB. It can make physical modeling easier as physical systems are now block elements, as in you no longer need to create and code your own blocks for a heat exchanger. That said, since you're not the one coding the functions of the block elements, there is a bit of a learning curve. At this stage, we thought we were close to a working model that uses custom elements from the MATLAB Rankine cycle library and two-phase fluid properties ported in from CoolProp. However, after increasing the sample time, the system dies at around 500 seconds. Definitely not a good, stable working model. Going forward, we're going to try and slowly probe the model from the ground up to see where this error is occurring. If, after March 15th, we are still stuck, we're going to build a model in Simulink using functions from the working fluid selection to create the necessary block elements. If this does happen, we would like to model the varying blackbody temperature by using the heat transfer model in Simscape from De Silva and Fernandez, shown here. And that's where Team Thermos is at today. We have made great strides in our hardware build and data analysis, and though we would like a more thorough simulation complement, we have a basic one that already shows the feasibility of our power plant idea. Simulation and testing are scheduled to be done by the end of March. The implementation of the pump driver should be completed by then as well. That leaves April for us to fine-tune our experiment and manage our results. If successful, Team Thermos will showcase not one, but two potential models for residential solar power. A diversification from photovoltaics by using solar thermal of equal size, and the possibility to generate power from your driveway. Thank you for your time. Please feel free to reach out to us if you have any questions.